So, hello everyone, and welcome to your second chemistry revision day. So today we'll be covering methods for separating mixtures. This is quite a big topic. There's lots of different ways to separate mixtures, and it comes up quite frequently in different exam questions. Okay, so it's a topic that's applied to many different areas. So firstly, let's start by understanding the difference between compounds and mixtures. Okay, so what is a compound? A compound, an example of a compound is, say, NaCl. So a compound has a fixed composition, which is really key. So you will never have Na2Cl. It is always NaCl. So that's what a fixed composition means. And so to separate NaCl, you need to separate it through another chemical reaction. So you can't separate NaCl by any physical methods. So also, please, could you put any answers in the chat function and any questions in the question box? And I've seen a mixture would be air. So air is an example of a mixture. Brilliant. So today's topic is on separating mixtures. Okay. So so to separate a compound, you must do it by a chemical reaction, and chemical bonds, and there are chemical bonds between the atoms in a compound. So here we have sodium chloride, and there are chemical bonds between the sodium and the chloride. So it's not really easy to separate compounds, and we don't really need to know how to separate them. However, you do need to know the difference between compounds and mixtures. Okay, so then let's talk about mixtures. What is a mixture? So our mixture, they have no fixed composition. So if, say, in an example would be, say, sand in water is an example of a mixture, right? So if we, say, had this much sand in the bottom, that's a mixture. But also, if we have this much sand and then in the water, that's also a mixture, okay? So the composition can be varied significantly. So it's much easier to separate mixtures. You separate them using different physical methods, which is what we're going to be talking about. And there are no chemical bonds between the substance. Therefore, you don't need to separate with these chemical reactions, making our separation much easier. Okay, any questions about mixtures? Is cake batter a mixture? Yeah, it is. There's not chemical bonds between your ingredients. So brilliant, that is a good rock salt. Yeah, that's also a mixture. Great ideas. And can anyone name a compound then? Does anyone name a compound? Yeah, perfect. Water compound. MgCl2 it would be. But yeah, brilliant. Iron sulfate, carbon dioxide. Perfect. Lots of great examples. Well done, guys. Okay, so you guys understand the difference between a mixture and a compound. So MgO, brilliant. Carbon dioxide, great examples. So now let's talk about some physical methods to separate mixtures. So we're going to be covering filtration, which is to remove insoluble substances from a solvent. Crystallization, which is where we have a solution. So therefore, we're separating something that is dissolved in water. So we're removing water to get back to our solute. Okay, and then we've got distillation, which where we're going to evaporate the solvent first and then condense it. And that allows us to collect the solvent. Okay. How do you separate compounds? So separating compounds is a lot more tricky, and it won't be covered in this course, but that will be in your electrolysis topic when you do it at school. So you need to do chemical reactions to separate compounds. That's why it's a lot harder. Okay. So let's talk about filtration first. So how does it work? We have the funnel, but if we just poured our mixture in here, it is salt, sand, salt in salt solution. Okay, so here we've got a mixture of sand and salt solution. Okay, so firstly our method is to get rid of the sand, because we're able to do that by filtration. Yeah, so this is a cool practical, yes. You should be doing it in school at some point. We won't be covering electrolysis as we don't have that much time, and there will be a Kahoot soon. Yes. Okay, so let's look at our filtration process. So we've got a filter funnel, but if we say poured our sand and salt solution through the funnel, sorry, what would happen? Our sand would also go straight through the funnel, and therefore we don't have any separation. So we must have filter paper. This is what captures the sand and stops the sand from going through into the salt solution, going through the funnel. Okay, so the sand is left here in our filter and the salt solution flows through. Yeah, so that's how you separate anything insoluble from your solvent. Okay, you get your filter paper and your funnel and you just pass the liquid through it. Yeah. So now let's see crystallization. Okay, so with crystallization, this is now how we're going to separate our salt solution. So here we have our salt solution, and of course we know that salt is a solid to begin with, right? You should have seen salt in your houses, and what you say, add to your fish and chips. So yeah, so we've got a solid that is dissolved in our water, in our solution. Okay, so how can we get back this solid? So the way we do it is we evaporate the water from our salt solution to leave our crystals. Okay, so you evaporate the water until you start seeing crystal formation, and then you leave the rest of it to evaporate on its own without heating. Okay, so here we've shown that we've heated it. So we heat up the water becomes steam, and then the steam heats up this salt solution, which allows our solvent to evaporate and leave behind our solid crystals. Okay. During crystallization, do we need a gauze? So that depends on your experiment. So say if you had your Bunsen burner, so yeah, here you would have a gauze on this heating mantle thing. Okay, underneath the beaker to hold it up. So we're going to do distillation now. Let's move on to distillation then. So that is your crystallization to get rid of. Yeah, so in the copper 2 oxide practical, you do crystallize. Brilliant, well done, great example. So in that practical, you evaporate the liquid and then you move it to a watch glass and let the rest of the liquid evaporate, and you get your lovely crystals that are blue. Yeah, brilliant. Hopefully a lot of you guys do the copper sulfur experiment. Okay, so distillation is fairly similar to crystallization. Once again, we're evaporating the solvent. However, this time we collect our solvent at the end, okay? So we evaporate. So now this is a salt solution. For example, the sea is a salt solution, okay? And in some countries, they want to collect the water from the sea so that they have nice, clean water. So to do that, they can distill the water, so by evaporating off, and then they collect it in collect the pure water, as all that comes through is your water part of the solution. So yeah, the topic today is separation, so separating mixtures, and we will be doing fractional distillation after this. Would you just use distillation if the desired product is in the solvent? So yeah, so distillation, so if you don't want to keep the solvent, you can just do crystallization, okay? But if you want to keep the solvent, then you use distillation. So in this case, we want to collect pure water. Say it could be because we want to drink it. So in that that's when you distill, because you want to collect the solvent. You don't want it to go to waste, as opposed to if you evaporate it, it just goes into the atmosphere and just leaves, so you don't have any solvent remaining. Okay. So yeah, this is simple distillation, and we'll be covering fractional distillation very soon after this part. So some key components of our distillation apparatus to note is firstly the condenser. So do people have any idea what the condenser does? What is the function of this condenser here? Yeah, brilliant. It condenses the water vapor to cool the gas so it turns back to water. Exactly, okay? So as we can see here, it has water in and here's water out. So you're pumping through the condenser cold water the whole time. This allows any vapor that comes through the condenser to condense back into the liquid. So in this case, we have water vapor coming through here, and of course it cools down, and that's how we get our water at the end. Yeah, and it's really important to know that the water comes in at the bottom and out at the top. This ensures that the condenser is always filled with water, and so the cooling of the vapor is the most efficient it can be. Okay, any questions on these three separation techniques? Would large-scale crystallization contribute to global warming? Probably large scale, but in industry, the techniques used are quite different to the techniques learned at school. Okay, but everything basically contributes right now. Are these core practicals? Yeah, you should be doing them at school. How does salt not evaporate? Okay, great question. So of course, salt is what is salt at room temperature? As we know, it is a solid, right? So to evaporate, it must be above its boiling point. Okay, so the boiling point of salt is really, really high. Even just the melting point is really high, as like we always see salt as a solid, right? So the salt does not evaporate as the temperature you're heating it to is not above its boiling point, which is what you need for evaporation to occur. Okay, does that make sense? So by evaporating the liquid, it leaves the solid behind, okay? So of course you have the solid dissolved in the liquid. What is the definition for distillation? So I'd say distillation is heating up, evaporating your solvent, and then condensing it and collecting it. Okay. Is this a repeated lesson from yesterday? No. This is to do with separating mixtures. And yesterday we were doing chemical equations and atomic structure. Okay. So yeah, as we've seen, with sand and salt, we have three things to separate. How would we separate the sand? Firstly, so sand is insoluble. We're going to use filtration. And then to separate the dissolved salt in water, we either use distillation or crystallization, depending on if we want to keep the solvent or not. Yeah, does that all make sense? Let me look at the questions. I was supposed to draw this out. So actually in questions, sometimes it is asked to draw it out. There's been questions where you have to draw out the apparatus and you have to label them. So it's really good to know all the, to know which is the condenser, which is where the water goes in, where the water goes out, the fact that there's this thermometer. And the temperature on the thermometer is always the boiling point of the substance being heated and evaporating. Okay, so on this, when it's water, it would read 100 degrees Celsius, because that is the temperature that water boils at. That is the temperature of the steam here. What do you separate distillation for? I don't really understand that question. Okay. So will the boiling point increase when? So those are some of the methods for separating stuff physically. So now let's look at another type of distillation. So what we just looked at was simple distillation, okay? And now we're gonna do some work on fractional distillation, okay? So this is slightly more difficult and requires slightly different equipment, okay? So firstly, fractional distillation is used when you have miscible liquids. So we want to separate mixtures of liquids, okay, that can dissolve in each other. That makes them miscible. So if a liquid can dissolve in another liquid, that means that they are miscible liquids. Okay, and we use fractional distillation to separate these liquids. So yeah, so the liquids in the solution have different boiling points, and that's what allows us to separate one from the other. Okay. Sorry, I'll look at the questions quickly. Is fractional distillation also in the alkane organic chemistry topic? Yeah, perfect, well done. So I'm going to link fractional distillation to that topic in a sec. Yeah. Okay, so we've got, so with our fractional distillation, we have a fractionated column, which we're going to see in a sec what it means, and that aids this separation. So in our miscible liquids, we're going to have, say, two different liquids with different boiling points. The liquid with a higher boiling point condenses first, and the one with the lower boiling point condenses later on. Okay. Higher or lower it to be fractional distillation. So good question. Does the boiling point need to be at least 1 degree higher or lower for it to be fractionally distilled? So you do need a difference in boiling point. A 1 degree difference is probably good enough, but that will be for industrial separation at school. So you probably wouldn't even do this experiment, but it's much easier to separate liquids with a larger difference in their boiling point. So if you evaporate ethanol from water, is that simple fractional distillation? We're actually going to see that example next. Okay. So let's look at this example. So this is what we call our fractionating column. As we can see, it's quite long. Yeah, so this is what helps us separate the two mixtures from the two liquids from each other. So in this case, we have a mixture of ethanol and water. So these are miscible liquids, as you can see. We've mixed it completely here. And so now we're trying to separate them. So the boiling point of ethanol is 80 degrees. Okay. And the boiling point of water, as we all know, is 100. Okay. So that it makes it, they've got a fairly good difference in their boiling points. So we will evaporate our liquid and it's going to go through into the fractionating column. So a key thing to note with the fractionating column is that at the top, it is much cooler than at the bottom, okay? So your liquid with the higher boiling point condenses here at the bottom and just goes back down into your flask. So which has a higher boiling point, water or ethanol? So as water has a boiling point of 100, it's going to condense somewhere at the bottom of the fractionating column and fall back in. However, as the ethanol has a lower boiling point, it's going to stay a vapor for longer and it's going to reach the top and go to be distilled off. Okay? Because at the top it's much cooler. So water is unable to go to the top. Yeah, we will look at some exam style questions on this. What would you do if the boiling point are very close to each other? You wouldn't be given an example like that. You will always be able to separate them. If you evaporate ethanol from water, yeah, sorry. No. It's very similar. Okay. So is fractional distillation used only to separate two liquids or more? So you can separate a lot more with it. So that's part of your organic alkene chemistry. How do you tell the difference between simple and fractional? Okay, so simple you use when you say you got a solution like salt and water, as we just saw. Fractional is used in when we're separating miscible liquids. And in your fractional distillation, you have this fractionating column. Okay, that's the key difference between simple and fractional distillation, okay? And the main thing to remember about the fractionated column is that at the top it is much cooler than at the bottom. So at the bottom it's much warmer. And as I say at the top, the temperature is going to be significantly lower than 100 degrees Celsius. The water will have condensed and fallen back in. However, because the ethanol has a lower boiling point, it carries on and it is able to go through the condenser and form your product, form your ethanol, your pure ethanol. Okay. So would water and ethanol together would make a compound? No. So water and ethanol together make a solution. Okay, so they are two miscible liquids. So what it means is that, say, ethanol, just like you can have your salts. So when you add water to salt, it doesn't just stay in the bottom, it dissolves into your solution. However, when you add water to sand, the sand does stay in the bottom of the solution as it is not soluble. It does not dissolve. So sometimes, hopefully some of you would have seen at school, oil and water. So the oil sits at the top and the water sits at the bottom. Okay, so these two are not miscible liquids. The oil does not dissolve in the water. However, in the case of ethanol, the ethanol does dissolve in the water, and that makes them miscible liquids. Okay, so when you have water and ethanol, you have a solution. The ethanol has dissolved in the water, and that's why we must separate it using this fractional distillation. What separation technique is used to separate oil and water? That's not actually covered at GCSE, but it's to do with a separating funnel. So because you don't have it dissolved, you can see a line where the two meet. So you can just run the water through, and you get rid of the water and you just leave the oil. It's really easy to separate oil and water as they can't mix. They don't dissolve in each other. So it's much easier for this method, okay? So yeah, so now let's look at an example in the crude oil case, okay? So here we pump in our heated crude oil, okay? And here it's vaporized. It's all of them are now a gas, okay? So this crude oil, it goes up into the fractionated column. And as we can see, look, there's a temperature gradient. So at the top, it is much cooler. And at the bottom, it is much hotter, okay? So in the crude oil, you've got lots of different alkanes, lots of different liquids that all have different boiling points. So some of the crude oil, it has really, really high boiling points. So they condense at the bottom of the fractionating column. Okay, so high boiling points condense at the bottom. That's a really key factor, remember. Bottom of the column, okay? And then those liquids that have a much lower boiling point, they continue to rise. And as they reach their boiling point temperature, they condense. So if there's a liquid that has a boiling point of around here, temperature-wise, it's going to condense onto this plate thing. And then those who have an even lower boiling point are going to condense here. Those who have an even lower boiling point will condense there. So this is cooler and that's hotter. Okay, I'll just get rid of the questions. Can we separate gas? Yeah, you can. You can do that also with condensation and distillation. Okay. And yeah, low boiling point liquids go to the top of your fractionating column. Brilliant. So, okay, does that make sense? And hopefully, some of you may have already covered the alkanes topic, and some of you will be covering it, and this will become clearer then. So this is really a very, very useful method for separating crude oil into different fractions. And it's really key for the oil industry. And so, yeah, it is separating liquids based on different boiling points that they have. BPs. Okay, so any other questions on fractional distillation? Cooler BP condensed. You said that the cooler, so the higher BP condense at the bottom. Okay, so those liquids with higher boiling points condense at the bottom. Those with lower boiling points condense at the top. Okay. Okay, I'll quickly go to the introductory side of fractional distillation. Quantitative chem. So we won't be covering quantitative chem, not in these lessons. Okay, so here was the introductory thing. Yeah, brilliant. So bitumen has a high boiling point. Perfect. So that's what is shown here. So this thing at the bottom is going to have a really, really high boiling point. Look, it's condensed super low, where the temperature would be super high. Okay, so it's going to have a very high boiling point. Great. And of course, petrol is going to have quite a low boiling point. Okay. Okay, so now let's move on to paper chromatography. So hopefully some of you guys have done the paper chromatography practical. It's quite cool to see. So what is paper chromatography? So with paper chromatography, we can separate mixtures of solution. Okay, so say ink. Ink is a great example of a solution. Yeah, so say if we have, what we're going to see an example. So say if we had like purple ink, you make that from blue and pink, no, blue and red, sorry. Yeah, so that is a mixture of blue and red solutions. Okay, so we want to separate sometimes these solutions to find out what compounds are in it. So how do we do this? So it works because some compounds in our solution, in the mixture, dissolve better than others in solvent. So the relative solubility of components making up the mixture in the solvent determines how far they travel up the paper, okay? So the more soluble a substance is, the higher it travels up the paper on paper chromatography. So I think some examples will be very helpful to visualize this, okay? So here we've got an example. Here we have our orange dye and we've got a blue dye. So we can see, so by using paper chromatography, we can separate this mixture that has made the orange dye into its two colors, okay? So that lets us understand what two substances have gone in to form our orange dye. So we put it in, so we dot on our line. So firstly, we start off by drawing a line. And can people tell me why must the line be drawn in pencil? Do people have any ideas? Why must you use pencil to draw this first line? Yeah, brilliant. I can see some really good answers. Yeah, so pencil does not dissolve in your solvent. Of course, you don't want a substance that does dissolve in your solvent, as it's going to get carried up by the solvent, and you're just going to get a very messy result, okay, which is not what we want. So yeah, so we always write our line in pencil, and then depending on the relative solubilities of our different compounds in our mixture, they will travel up the paper to different levels, okay? So in this case, for the orange dye, which one is more soluble in our solvent, which is water? Is it the red or is it the yellow dye? Brilliant, okay, some great answers. So red is much more soluble in the solvent because look, it travels much higher than the yellow dye. So yeah, so that's most soluble travels up further, and it allows us to separate these mixtures. Great. There's quite a lot of questions. You need to learn the practicals. You don't need to learn specific practicals, but you need to understand what you're doing is sometimes we do have questions on practicals, and yeah, we are going to work out the RF values. You're going to learn how to do that. Yeah, some really good answers to all the questions. Well done. Okay, so yeah, brilliant. So the way that paper chromatography works is you put on your mixture on the dots, you dot your mixture onto the line, you put your paper in a solvent, and the solvent carries up the different compounds and separates them that way. Okay. And of course, because of the different solubilities in the solvent, they get separated, and that's more soluble gets carried further up the paper. Okay, so look, this is another example. In this example, we can see we have separated our mixtures, and we can see that both purple and green have the same compound in them, our blue dye. Okay, so compounds that are the same have the same retention, have reached the same point on the paper. Okay, so paper chromatography not only allows us to see the different compounds in a mixture, but it also allows us to decide upon which two mixtures have the same compounds in them. Okay, so as we can see, both of these contain blue dye. So let's talk about how we do our RF factor. Okay, so RF factor, does anyone know what it stands for? Any idea what RF stands for? Retention factor, brilliant answer. Perfect. So yeah, RF is the retention factor. And how do we find the retention factor? So, do you know? Yeah, great answer. Substance travelled over solvent travelled. So in the question, you will see a line up here. And this is called your solvent front, okay? So this is the line where the solvent has reached. So if, say, the compound has travelled there, the solvent will have travelled to the top, this line, okay? So to work out our RF values, we find the difference travelled by our substance, by our compound, and we find the distance travelled by our solvent, okay? So we're going to call this one A, we're going to call that one B. So to find the retention factor for our blue dye, we do A divided by B, okay? So that's going to give you a decimal point, and that is your retention factor. I thought the colours and joint. Sorry, I don't really understand your question, Shrenik. I thought that the colours are and joined, and it stops with the new colour going up to them. Okay, we can write down the equation of words, of course. Is it because red is a pure colour, whereas yellow is a mixture? Okay. Do we need to memorize the equation? Yeah, so it won't be given to you. You need to know how to find the retention factor. Okay, so yeah, so the retention factor in words is distance substance has travelled. So RF equals distance substance has travelled divided by distance solvent has travelled, okay? And of course, on this is slightly hard as we don't have a ruler, but at school, if you ever ask the question, you measure your distance that the solvent has travelled. So this is the solvent front, this is where the solvent has reached. So you measure this distance, which is B. So to link A and B to this word equation, this is A, the top part's A, and the bottom part is B, okay? So yeah. So we get a ruler, we find out how far our substance has travelled, and we find out how far our solvent has travelled, and we divide one over the other to find out our... Is this in the ACO syllabus? Yes, it is. It's quite at the start of the ACO syllabus. Can the RF value be bigger than 1? No, it is always smaller than 1, as the solvent always travels further than your substance, okay? So your solvent will always be higher than your substance, so the RF value will always be smaller than 1. Is the solvent always water? Probably for the case you will see, yes, it is. Okay. So yeah, so in your exam, you should be given, well, you would have a ruler and you'll be able to find the distance that the solvent has traveled and the distance that the substance has traveled, okay? And you need to remember that this line at the top, the solvent front, is where the solvent has reached. So there will always be a line. Okay, so now let's look at this one. Let's call this one B. So in A, can we see that substance A has been made up of one of B? Okay, so these two are exactly the same substances as they have the same retention. So they've traveled up the same distance. So that tells us that they have a substance that is the same. Do you need units? No, you don't. It's just a number. Good question though. Okay. So let's see more examples then. So if we have these as A, B, and C, which two substances are the same? Yeah, great answers. A and C, because they have traveled the exact same distance on our paper perfect. So paper chromatography is really good at identifying which compounds are in both substances, okay? Not only is it good to separate and see what compounds it is, but it's always great, also great to compare. Yeah, they have the same retention. Brilliant, great answers, guys. Dun, dun, dun. So R stands for retention factor. In words, it means retention factor. Okay. So I think it's now time for our Kahoot. Okay. So if everyone wants to get Kahoot up, just go to the website and we're going to get the code up now. And if you guys don't have access to get Kahoot, then please just write down your answers and just mark them as we go along. After our Kahoot, we're going to go with the answers and then we are going to do some past paper questions on this. Okay. So if everyone's ready for the Kahoot, does anyone have any more questions on paper chromatography before we start? Okay. Dun, dun, dun. Okay, so can everyone see the pin? I'll copy it into the chat. Brilliant. So we'll give it a minute. Oops. So it's in the chat as well if anyone wants to see them. So we'll start it in another 30 seconds. So yeah, Okay, so 10 seconds and we're going to start. Okay, let's start then. Oh, people still joining. Okay, we're going to start now. So if you've been unable to join, just write it down on some paper, your answers. Okay, let's go. Almost done. Great. Okay, so yeah, it is cooler. The bottom is warmer, the top is cooler. So the next one then. Well done to Boris Johnson, 2.9. At the top. So which is not true about mixtures? So remember, it's not true, which is not true. Yeah, well done everyone. So there are no chemical bonds between the different substances. Oh, well done to Boris Johnson with keeping his first place. Okay, so number 3. Filtration can be used to separate Okay, brilliant. So yes, salt and water caught some of you guys out. We're going to go through the answers at the end after this. Oh, well done for keeping that top place. Well done, everyone. Okay, so salt and water is a compound. Almost there. Is salt and water a compound? Yeah, brilliant. Well done. Majority correct. So go through it at the end. Oh, we've had a bit of a change on the leaderboard. Well done, guys. So how does paper chromatography separate substances? So perfect, yeah. They have different solubilities. So although sometimes they have different colours, they get separated because of the difference in solubilities of those colours. Wow, well done. Boris Johnson's kept the top position for the whole time. So how many different substances are present in A? Do you think? Yeah, brilliant. Majority correct. So, although actually it's quite even between 3 and 4, so we're going to understand why it's not 4. Okay, so third place, Cassia, well done. In second, I'm in Maddie, and in first, well done to Boris Johnson 2.0. Great effort, guys. Yeah, runners up. Okay, well done. So now let's go through our answers. So let's go through the Kahoot quiz then. So firstly, fractional distillation. What do we learn about it? Yeah, so in our column, the top is warmer and the bottom is cooler. And those with a higher boiling point condense at the bottom, high BP substances, and those with low BP go to the top. Okay. And then, yeah, here it is much cooler. Okay. So then next one. So what's not true about mixtures? So yeah, we've learned loads, well, a couple of different physical methods to separate mixtures through. And of course, there are no chemical bonds between substances. That would be correct. As we know that compounds have chemical bonds between them, not mixtures. And they don't have a fixed composition, and sand and water is a mixture. Okay. So then, so when do we use filtration? So we use filtration to separate an insoluble thing from water, right? So some of you guys press salt from water. Why is that incorrect? Although salt, as you see, it is a solid, it is soluble in water, therefore it dissolves, and filtration it's not able to separate salt from water. So filtration is not able to separate anything that can dissolve in water from water, okay? So that's why we must use either distillation, or crystallization to separate our soluble solids from water. Okay, so oil and water would not be separated by filtration, as they're both liquids. Although they don't mix, they would both run straight through the funnel. However, sand from water, as sand is insoluble, we would be able to separate it, as it will not be dissolved and it will remain in the water. And of course, sugar from water is like salt in water. They both dissolve, they're both soluble, and therefore neither of them can be separated by distillation, by filtration. Okay, salt and water is a compound. No, it is not. Salt in water is a mixture. So salt by itself is a compound, and so is water, but salt and water are a mixture. That would be false. So paper chromatography can separate substances because of their different solubility in the solvent that runs up the paper, okay? So of course, that's what carries them through the paper, and based on their solubilities, they travel to different lengths on the paper. So yeah, we don't look at melting points in this case, and they might have different colors, but we don't separate them because they have different colors. Okay. So then, last one. Oh, so let's go back to the slide with the same one. Okay, so this was the same example as C. So how many substances are present on A? So there was quite an even split between 3 and 4, okay? So this is our mixture. This is not a pure substance. So when we count up the dots, we ignore this one, okay? So we have separated 3A into 3 separate dots. That means that we have 3 different substances. We have this that's one type of substance. We have this one that's another one. And we have this one that's our third one, okay? So although you see 4 dots, we have only 3 different substances in our mixture, as A is separated into 3 separate dots, okay? So for example, in our purple mixture, how many substances do we think we have? Do people want to write that down? Yeah, exactly, great. I can see some good answers. Yeah, some correct 2s. Brilliant. So we've only got 2, as we've got blue and red, and we've only got 2 dots that have appeared. Okay. So yeah, so that's how you realize how many is in the thing. So now let's try some exam questions. Okay, so let's grade through 4. A student used chromatography to find out which colorings were used in her favorite sweets. Diagram shows some of her results. So give the color of a sweet which contains only one coloring. So do people want to write their answers down? What has only one coloring? Yeah, brilliant. Red and yellow. Both of these only have one coloring, as we can only see one dot on them. Exactly. Okay. So one dot means one colouring. So name two sweets which contain one of the same colouring. Yeah, brilliant. So it could be red and purple, as they both contain red, as we can see here. And it can also be green and purple, as we have it here. However, I've just seen a red and green, okay? So it couldn't be red and green, as this dot is not in the green one, okay? So for you to have the sweets containing the same color, you need to have two that have the same retention, okay? And therefore it would be yellow and green. Brilliant, perfect. So yellow and green is also an example. Great, okay. Fill in the results you would expect to see for the orange sweet. Okay, so what colors would we expect to make up the orange then? Yeah, some great answers. So we would put two dots in the same position as red and yellow. So one, say, around here, and one around here. Perfect. Yeah, brilliant. Okay. So give two uses of chromatography. So what could our use of chromatography be? So one of them, which is obvious, is to separate the mixture. Okay, so someone doesn't get the orange question. So with the orange sweet, we firstly think, what colors make up orange? Okay, so we say that orange is made from yellow and red. So therefore, the orange sweet will have yellow colouring in it, and so we'll also have red food colouring in it. So that's why we draw a dot here, because that is where the red part of our orange sweet is. That's what, like, the separation of that. And then up here is our yellow part. Okay. Does that make more sense? Okay. So one of the uses of chromatography is to separate the mixture, yeah? And the other one is to analyze what a soluble solution is made of. Good answer, yeah. So one is to separate, and another is to say analyze, to compare two solutions together to see if they have the same substances in it. Okay, so a great one is analyze as well. Okay, so name two phases when performing chromatography. Could use it to check blood groups. Yeah, they probably do use it to check blood groups. Great. Haven't heard that. I think they would. So do we know the two phases when performing chromatography? Does anyone have any idea? Yeah, brilliant. So we do have a stationary and a mobile phase, okay? So let's look back at an example. So we look at this one, right? What is our stationary phase in this case? What does the stationary phase mean? So it means, so the stationary phase is actually the paper. So that's not moving. What's moving up? So the mobile phase is our solvent. The solvent is moving up the stationary phase, okay? Yeah, the mobile phase is the solvent and the stationary phase is the paper, as that just stays still and allows the mobile phase to move up along it. Yeah, okay? So usually, well, in paper chromatography, it's always the paper is your stationary phase and your mobile phase the solvent. Not really. So so the pencil isn't a station. That's just like something to help you. You just draw the pencil to let you like see where the line is. Your stationary phase is whatever the thingy is moving up on. Okay, which is your paper. Okay. So let's look at the next question then. Dun, dun, dun. So complete the equation. Who can remember the retention factor equation? If you want to write that down. Yeah, lots of great answers. Yeah, brilliant. Distance. Yeah, great. Distance moved by substance over distance moved by solvent. Yep, perfect. So if we had, this is a very rough example. So we have this, oh, we've got one dot. So it would be this distance A divided by this distance B. So what the substance has moved over the solvent has moved. Okay, brilliant. So how will a pure compound look when run on chromatography paper? Okay, so if we just had a pure compound, what does that mean? What other forms of chromatography is there? You only need to know paper chromatography. Other chromatography is university chemistry level, so you definitely don't need to know that. Yeah, so if we had a pure, it would look as this example I've drawn here. It's just going to have one dot on it that has traveled a certain. So you're just going to see one dot on the paper. You're not going to see any more. Yeah, brilliant. So that's what it means. A pure compound just means that it's made of one substance. So you're not going to get separation. You're just going to have one dot present. Oh, relevant. Okay, so this is quite good. Study the chromatogram and match the dots on Y to the other dots. Then work out what substance Y is made out of. What is substance Y? Okay, so let's figure out what is substance Y made out of. So what are of the other stuff? So let's try and match up the dots. Yeah? E and D. Yeah, perfect. Some good answers. Yes. So yes, E, F, C. Okay, so it couldn't be EFC because can you see this dot and this dot are not present in white? So if it was EFC, you'd need these two dots as well. Okay, so although EFE, so it also can't be F because this dot is not present here. Okay, so although some of your dots, these suggestions have matched up, so this dot does match up, you don't have anything that matches up this. So yeah, the only answer to what is Y made up of is D and D, okay? So because these two match up perfectly with the others. This one matches with this one, this one matches with this one, and this one matches with this one. Although in other substances between A to F, there are dots that do match up. So this one does match up with this one. But we don't have a dot that matches up this part of C, so therefore C cannot be one of the substances that made up Y. Okay. Does that make sense? Why it's only D and E? Yeah. Is that clear to everyone? This was quite a confusing question. So does it have to match up both dots on Y? Yeah, it has to match up all three dots on Y, and you can't have any other dots present in your option, okay? So like it can't be C, because although this dot at the top does match up with the top at the top, the dot at the top of Y, we don't have any dot that matches up this one or this one. So therefore we know it's not C because Y doesn't have this substance or this substance, okay? So they must match up, but also there must not be any other substances present in your option. Okay. So I think we'll finish off on this question then. Any questions about this? Any last questions on this topic? No? Okay, well, we'll finish up here then. Have a lovely rest of your day, and I will see you guys tomorrow again at 11, I hope, for our next revision class. Bye.